So let's try a tougher synthesis problem. Here we're only allowed to use propene as our carbon source. We have 3 carbons here, and we're asked to synthesize hex4ene3ol, which is this hexanol compound here. And because we have hex, of course we have 6 carbons. Now it isn't obvious which steps we should take to make this, but there are 2 clues that we should note. For one, this is a secondary carbon. The second clue is that we have the trans isomer here for this alkene. It's the E isomer, in other words. So we should think back to all the reducing methods we have and all the reagents that we use to reduce alkynes. In part 1, we discussed catalytic hydrogenation. That takes us all the way down to an alkane, no degrees of unsaturation. So we can't use that. If we use Lindlar's catalyst, this methyl group would be projecting upwards like this. So that would be the Z isomer. So the only reducing method left that we've covered in the alkyne chapter is sodium dissolved in liquid ammonia. And up until now, the only possible nucleophile is the alkynyl anion, which we derive from propene, so it would be 3 carbons. If we react that with another 3-carbon electrophile, we can form this compound right here. The question is, what is that electrophile? Now we said one of the clues was that this is a secondary carbon. In part 1, when we had a tertiary alcohol, we used a ketone, and that's why we had the methyl group right here in part 1. But here we have a secondary alcohol. And if we trace back carbons directly attached to the alcohol, 1, 2, and 3, it looks like this was a derivative from an aldehyde. Something similar to this. So if we synthesize a 3-carbon aldehyde and a 3-carbon alkynyl anion, mix them together in an aprotic solvent, we could form this compound here. But that would be the alkyne. We said that sodium dissolved in liquid ammonia would be the choice of reduction, again because it's the trans isomer. Even though we have many steps, the goal is to generate the nucleophile, form an electrophile, mix them together, and partially reduce. Let's see if it works. So just like in parts 1 and 2, we'll take our alkene and carry out a 2-step reaction to form the alkynyl anion. So we start with propene, and we introduce bromine dissolved in dichloromethane. That forms this compound here, a vicinal dihalide. We then take the vicinal dihalide and react it with 3 mole of sodium amide base dissolved in liquid ammonia, and that will form our alkynyl anion. Now to form this 3-carbon aldehyde, we can't use the nucleophile here, so we carry out an aqueous workup to form the alkyne, and then we do a hydration reaction in the next step. So let's take our alkynyl anion and carry out an aqueous workup where we protonate that terminal carbon to form the alkyne. And now we need to carefully choose our next step. We have a 3-carbon alkyne, and the goal is to go from that to this compound here. Propanol. It's a 3-carbon aldehyde. It's anti-Markovnikov when we look at the alkyne structure here. The only way to do that is to carry out hydroboration. So we take our aldehyde, and then in the first step we use a borane derivative, dicyamyl borane, and we use an ether or other aprotic solvent like THF. And in the second step we use peroxide and aqueous base like sodium hydroxide. So we have our electrophile, which is the carbonyl carbon, and our nucleophile. So let's react them together to form this 6-carbon compound. So let's take our nucleophile, we'll call it compound 1, react it with our aldehyde, compound 2. And just like in part 1, we'll carry out the reaction in ether or other aprotic solvents like DMSO. And in the second step, we need to protonate the alkoxide to form the alcohol. So we carry out an aqueous workup. Now, this portion of the molecule comes from the aldehyde. Remember, it's protonated. And this portion comes from the alkyne. We should have 6 carbons. 1, 2, 3, 4, 5, 6. Now, the final step is to form the E-alkene. That's from this partial reduction. And we were saying we would use sodium dissolved in liquid ammonia, and that should give us the transalkene. So let's take this compound, our alkyne, and dissolve sodium in liquid ammonia, which should give us our transalkene, 6 carbons long, the OH group at carbon 3, and the alkyne is reduced to the alkene.